In molecular research, there is a very important question. How do we know whether a specific protein exists in our sample? Western blot is a technique that helps us answer this question. Today, I will share with you the entire Western blot workflow from the fundamental principle to each practice step so that you can clearly understand the process and perform it with confidence. Once you truly understand the principle behind it, you will be able to optimize your own protocol more effectively. If you find this content helpful and would like to follow more topics about molecular biology and laboratory technique, don't forget to like, subscribe, and leave a comment to let me know which topics you are most interested in. Western blot is based on two main principles. First, proteins are separated by size using polyacrylamide gel, also known as SDS-PAGE. Second, the specificity of antibody is used to precisely detect the target protein. The entire workflow can be divided into four main steps. Step 1, protein extraction and protein qualification. Stage 2, SDS-PAGE electrophoresis. Stage 3, transfer of protein from SDS-PAGE gel. Stage 4, detection of the target protein using an antibody system. At stage 1, protein extraction and qualification. Protein extraction is the first step to collect the total protein of the sample. Protein qualification is essential because if sample contain different amount of protein, the brand intensity later on will not reflect true biology difference, but simply difference in loading amount. Therefore, we commonly use Bradford or BCA assay to determine protein concentration at stage 2 at the SDS-PAGE. The goal of this step is to separate protein based on their molecular weight. I have already created a detailed video explaining this process, and I have links here if you would like to review it.
So nice.
At stage 3, protein transfer from gel to membranes. After electrophoresis, protein remain inside the gel. Based on my experience, maybe using nitrocellulose is not better than PVDF membranes. But it belongs to your experimental condition. However, the gel is not suitable for antibody reaction. Therefore, we need to transfer protein from gel onto a membrane. Usually nitrocellulose or PVDF. This process is called transfer. Transfer uses an electric field to move protein from the gel onto the membranes while preserving their separation by size. After this step, the protein is essentially printed onto the membranes and ready for detection. First, we prepare the transfer buffer and we put all of the membranes, all of the instrument and equipment inside the buffer in the container. This step allows our gel and membranes will not to be dry.
Wow!
The assembled order from bottom to top should be: first, white cassette plate, then sponge, then filter paper. Filter paper we can put one slice or two slices. It depends on the paper thickness. And then PVDF membranes. We should arrange them in correct arrangement. And then we put SDS-PAGE gel. And then filter paper, and then we have to remove the bubble, so we use that, and then we put sponge, and final black cassette plate, mean negative sign. Finally, secure the cassettes. Then insert the cassettes into the transfer tank, ensuring that the white side align with the red frame mean positive electrode, and the black side align with the black frame with mean negative electrode. Fill the tank with the transfer buffer up to the indicated level, close the lid, and start the run. To avoid overheating, which can damage the protein, we typically run the transfer at around 30 voltage overnight, placing the tank on ice if necessary, or at 0.35 mA for approximately 1 to 1.5 hours, depending on the molecular weight or of your protein interest. In blocking, before adding antibody, we must perform a block step. Nitrocellulose membrane can bind protein non-specifically. If antibodies are added immediately, they may bind across the entire membrane surface and produce high background signal. Therefore, we incubate the membranes in a protein-containing solution such as non-fat milk or BSA. These proteins set the non-specific binding site, ensuring that antibody bind only on the touched protein.
Yay!
Blocking is typically performed for 1 hour at room temperature using BSA per TBST or skim milk with TBST. In my case, I use an optimal buffer that requires only 5 to 10 minutes. During blocking, prepare the primary antibody specific to your protein of interest. I dilute the primary antibody in 1x BSA TBST according to the manufacturer recommendation. However, the optimal dilution may depend on whether your protein is highly or weakly expressed. For a weak protein, a highly antibody concentration may be required.
Aha!
In this sample, I use a ratio 1000 dilution, so I add 6 microliters of primary antibody into 6 ml of BSA TBST. After blocking, we cut the block buffer and wash membrane 3 times with TBST 1x, 5 minutes each. Then incubate the membranes with primary antibody solution. And typically, this process will be pushed in 4 degrees overnight.
So nice.
After incubation overnight with primary antibody, in the next morning we can pour that antibody inside one fire cone and can reuse later. Then we can wash dust membranes with the washing buffer 3 times, 1 time 5 minutes. During the washing time, we can prepare the secondary antibody in BSA TBST1X based on manufacturer recommendation. Here, I prepare the ratio 2000 dilution, so I will use 3 microliters secondary antibody with 6 ml of the BS80-BSD1X buffer. After washing time finished, we will wash the membranes. And then we will incubate the membranes with secondary antibody preparation. Commonly, this process will be conducted as the 1 hour in the room temperature. After 1 hour, we will wash the membranes 3 times, 1 time 5 minutes. Finally, we process to signal detection. We use enhanced chemiluminescence core ECL to detect the light signal produced. The secondary antibody is typically conjugated to host radius peroxidase called SRP. When ECL substrate is added, SRP catalyzes an oxidation reaction that emits light, which is captured by a chemiluminescence imaging system. Add the mixed ECL solution to membranes. ECL solution usually consists of 2 separate components, solution A and solution B, which are mixed as ratio 1:1 immediately before use. In this example, I mix 5 ml of solution A with 5 ml of solution B. Then we add the mixed ECL solution to membranes, incubate for 1 minute on shaker, and then capture the image using a chemiluminescence imaging system. I use a cytival imaging system which provides the excellent image quality. Western blot is not just a laboratory technique. Behind every protein band that appears on the membranes lie patient precision and hope of answering a scientific hypothesis. When we truly understand each step, from extraction and electrophoresis to transfer, blocking, and detection, we are not simply following a protocol, we are mastering our experiment. Thank you for taking time to watch this video until the end. In this busy world of research, the fact that you choose to stay and learn with me means a lot, and I sincerely appreciate it. If this video brought you value, even just one small detail that helped you optimize your experiment, please give it a like to support my channel. Don't forget to subscribe to my language channel so we can continue exploring molecular biology and laboratory techniques together. I will read every comment, and your feedback is truly my motivation to continue create highly content each week. Thank you very much, and I see you in next video.